Hello, guys. Let me know if you have any questions about anything or if you need any help with any of the problems or anything like that. Hey, what's up, Santino? Good to see you. Hope you're doing well. It's kind of weird. Next week is spring break, even though it's like we've been away from school for a while already. But I won't be posting anything next week at all. So yeah, so let me know if you guys have any questions or anything. Yeah, so we're returning May 5th, which is like a Tuesday. I think it's May 5th. Let me double check. Yeah, May 5th, which is a Tuesday. So I'm guessing like it's put on a Tuesday because they're probably having all of us teachers come in on Monday just to go to meetings and stuff like that. Yeah, so it's still over a month from now. And that's the earliest it could be. It could even be pushed later depending on how crazy things are getting. I've heard that probably within the next few weeks, like April 20-ish, sometime around then, it's going to be like at the peak in the United States, this whole COVID-19 virus. So it's going to get really bad around then, like late April, April 20 something. So the earliest we'd come back is May 5th, but who knows, it might even be later than that. So we'll just have to wait and see, I guess. Yeah, so let me know if you guys have any questions or if you need any help at all. Hopefully you guys are okay on supplies and stuff like that too, and toilet paper, hand sanitizer. I'm trying to just leave the house like once a week at the most, just to get supplies if I need it. But other than that, just kind of staying inside the whole time, just to be safe. Yeah, so let me know if you guys have any questions. Okay, yeah, so right, so that's the temperature that liquid becomes a gas. right? So a higher boiling point is just a higher temperature. So it would be the strongest intermolecular force, so hydrogen bonding. Because with hydrogen bonding, the molecules are all like really closely, tightly packed together. So like water, for example, one H2O molecule is really tightly packed close to all the other H2O molecules around it. So it just requires more heat, so a higher temperature in order for it to become a gas. Yeah, so it would be easier to boil something with a dispersion force. But yeah, the stronger the intermolecular force, the higher the boiling point. Yeah, no problem. Yeah, just because it's a force that keeps all these molecules really closely tight packed together, so they need more energy, more kinetic energy from the start moving around and separating themselves into becoming a gas. We're going to talk a lot more about heat in this unit, which would be after spring break. So yeah, because next week's spring break, so I'm not going to post anything next week. So I'll just put that down here. No. Oh, wrong option. Let's get rid of that. Okay. But then is it? Yeah, so we're finishing this unit this week with the test on Friday, and then next week's spring break, and then we'll have the thermochemistry unit the week as the math in this unit. But there is one concept towards the end of the unit that gets a little bit crazier. Just trial and error, kind of time-consuming stuff. But that's at the end of the unit, so we'll probably get there like late April, maybe early May. Probably late April. So cohesion is basically molecules' attraction towards similar molecules of the same substance. Um, and so it's basically related to intermolecular forces. So because of intermolecular forces, for example, water, because of the hydrogen bonding, each water molecule within like a cup of water, for example, they feel this inward pull towards each other, kind of like here. It's probably better to draw it. So like, yeah, with cohesion, they all molecules of the same substance. Because we know they have intermolecular forces, they feel a force of attraction towards one another, right? So having a bunch of water molecules together. Or easier if I just draw it as circles, actually. Let's just do that instead. Like little circles, basically. So it's kind of like, right, having a bunch of water molecules together. We know they have intermolecular forces, hydrogen bonding, and cohesion is just the attraction that molecules of the same substance feel towards each other. So it's really just intermolecular forces at work. That's pretty much it. Whereas adhesion is the force of attraction between particles of one substance with particles of another substance. So it's two different things. So with adhesion, it's always two different substances, but it's typically things of two different phases of matter too. So right, with cohesion, like water molecules here, these are just water molecules. I didn't want to draw the H2Os because it might look too messy. But because of intermolecular forces, they're going to feel a force of attraction towards other water molecules all around them. So it's really just intermolecular forces in action, whereas adhesion is between molecules of two different substances, typically two different phases of matter. So a good example could be like if you put a straw in the water, right? If you put a straw in the water, which is a solid, right, like a plastic solid, and water is a liquid, it's the attraction that those water molecules would feel with the solid straw. This is just an example. But with adhesion, it's in between molecules of two different substances, and typically two different phases of matter, right? Like a solid plastic straw, but then liquid water. It's the same reason why, I mean, with this example in mind, it's the same reason why if you put like a straw in like a cup and you lift it out, there's gonna be some droplets still on the straw. It's not all gonna be like perfectly smooth and dry. It's still gonna be a little bit damp, or there's gonna be some droplets on there. And so with cohesion basically happening at the surface of a liquid is what creates surface tension. So if cohesion, because water molecules are all pulling towards each other from all directions, that's what gives you tension at the surface, or that little I guess is the best way to describe it, just the tension on the surface that allows certain insects, for example, to walk on the surface of the water. So cohesion is basically, so tape and glue is adhesion. Yeah, so it's basically, molecules of two different substances, and typically from different phases of matter, exactly. So adhesion is molecules of two different substances. Cohesion, it's molecules of just that one substance type. Cohesion is really just intermolecular forces in action, because we know intermolecular forces do this anyways. If these are all supposed to be H2Os, like water molecules, we know their hydrogen bondings bring them close together, and so that just causes cohesion, basically. So cohesion is the same substance. Adhesion, it's two different substances. Yeah, let me know if you guys have any other questions or anything. All right, so something kind of like that. Like, we always see water droplets on like grass or straws, like dew in the morning, for example. This is adhesion. Adhesion because it's two different substances, right? You have a solid leaf and liquid water droplets. Oh, hey, how's it going? Doing pretty good, Kelly. Hope you're doing well too. Do you have your last period is probably now sixth period, I'm guessing. You have like seventh period free probably, so you can go home early. Maybe. I know you're in band, so maybe not. That's cool. That's, yeah, I've never, well, I mean, I went to a Catholic high school, so I don't know if it was different, or I never really had that opportunity. I always had to be in school until like the end of the day, but that must be pretty cool. I'm sure to get to kind of relax at the end of the day. Yeah, so let me know if you guys have any questions or anything. All right, see you later. Thanks for stopping by. Hope you and your family are safe. Yeah, so let me know if you guys have any questions or anything. Yeah, a bunch of gases. Oh, that's Dalton's law. So yeah, Dalton's law is the one where there's a sum. Graham's law is the one of the rates, right? So yeah, this one's Graham's law. Yeah, Dalton's law is the one that's the sum. And that's one thing I probably should have been careful with earlier on, because these V's aren't volumes, they're velocities. So yeah, it's a different V. It's not volume, it's velocity. But I'm sure you already knew that, so. Yeah, Dalton's law is probably the most straightforward of the gas laws. Yeah, so I don't know if you guys want to see any other examples, or if you want to go through anything else. But yeah, I'll also post most of the solutions. Oh yeah, sure. So it would be something where it's just basically comparing two different gases. It wouldn't even give you any like numerical givens. It would just be this gas and this gas. So you kind of have to think which one's lighter, and that's based on the molar mass, right? So for example, something like all right, so I'm just writing out the question. So yeah, it wouldn't really give you any numerical givens. So this is one I just thought of right now. So hydrogen and chlorine gas are mixed together and they're both diffusing. So which one diffuses faster and by how much? So you can pretty much answer the first question just by thinking about their molar masses. So the lighter one's going to diffuse faster, right? So hydrogen is just 1 times 2, so 2 grams per mole. Chlorine is what? 17. Well, I can't remember. I think it's 17 point something, or I might be getting that mixed up. Let me double check. It's going to be the slower one though. Chlorine's heavier. Chlorine, I think it's 17 point something, or the atomic number is 17. It's 35. Yeah, that's it. 35.45. All right, cool. So we know right away that hydrogen is going to be faster just because it's a lighter gas molecule, right? This is 1 times 2, so 2 grams per mole. This is 35.45 times 2. So that's like, what, 71 or something? So anyways, we know that we're going to have to use Graham's law. And so since I know which one is faster, which is hydrogen, I'm going to put the velocity of hydrogen on the top of that fraction. And then, of course, you have to switch them on the other side. All right, so this is just me using the variables in the equation. I know hydrogen is going to be the faster one, right? I already know that answer because it's just a lighter gas molecule. So since it's going to be faster, I'm just going to put it on the numerator just to mathematically make it easier. It doesn't really matter. It could be on the denominator as long as the molar mass is in the numerator over here, as long as you're consistent with the fact that they're the same elements properties are like diagonal from each other. They're not straight across, right? So you could put it down here. I just put it in the numerator just to make it easier, just so I multiply the velocity of chlorine on both sides. All right, so hydrogen's on top because it's lighter. You didn't have to do that, but I just do that. And so anyways, let's go ahead and see what we get over here. I'm just going to get the velocity of hydrogen by itself, which is the square root of the molar mass of chlorine over the molar mass of hydrogen times the velocity of chlorine. So that squared, and this is 1 squared, not squared, times 2. Getting myself mixed up, sorry. 35.5 times 2, and this is 1 times 2. All right, so I just have the equation on the left side, right? So I know hydrogen is going to be the quicker gas, so I just put on the numerator up here. So let's just solve for the velocity of hydrogen because it's saying by how much. So what factor is the lighter gas? By what factor is the lighter gas faster than the slower gas? So multiply the velocity of chlorine on both sides. So just get it over here, and then just plug in your values. So the molar mass of Cl2 is chlorine times 2, so 35.5 times 2. And then hydrogen is 1 times 2, right? So I just have that down here. I almost made it squared for a second there. So if hydrogen then is the square root of 71 over 2 times chlorine. 71 over 2. It's just going to be 35.45 again. 35.5 times 2, 71 divided by 2 is just going to be the same thing again, to the square root, to the 1/2 power, 5.96. All right, so I did that first. I did this second. And then that just looks way too messy, sorry. I should get like a big whiteboard instead of a small one. But yeah, so I solved for the velocity of hydrogen here. I just multiplied the velocity of chlorine on both sides, so it cancels here. It's over here now. Molar mass of chlorine is 35.5 times 2 because it's Brinkelhoff, right? It's Cl2, not just Cl. So that's why it's up here. And then H2 is also in Brinkelhoff, so that's why it's not just 1, but it's 2 times 1 or 2. So then you basically have the molar mass of 70, you have a square root of 71 over 2, which is again just 35.45. And the square root of 35.5 is about 5.96. Yeah, 5.96. So the answer would be 5.96 times faster. So yeah, the first question would just be hydrogen, because it's the lighter particle. And the second question, by how much, it would be 5.96 times faster. Right, so that's pretty much like your final answer there. 5.96. All right. So that's basically how much faster it is. But yeah, let me know if you have any other questions about that. So it kind of goes over here first. This is me getting it by itself, plugging in the molar masses, then just multiplying that by 2, multiplying that by 2, and take the square root. So yeah. So yeah, this kind of question probably won't have any numerical givens at all. You would just have to look at the periodic table to know the molar mass. And then, of course, just remembering that these are in Brinkelhoff. because it might not say H2 and Cl2, it might just say hydrogen and chlorine. So then you have to remember, okay, those are gases that are part of Brinkelhoff, so they're diatomic molecules, so it's not just H, it's not just Cl, but it's double those. All right. Yeah, let me know if you have any other questions, though. Oh, yeah, true. Yeah, very, very dangerous. There's a lot of like household items and stuff that are pretty dangerous to mix too because they could create chlorine gas. So it's a pretty dangerous molecule for sure. Yeah, and I know. Yeah, it was definitely used during World War I, and I know what's it called? Mustard gas is mostly made of chlorine, but it's also with sulfur as well. It's a big compound. Yeah, we're probably not going to have time to get into this stuff, unfortunately, but this is an organic compound. So this is mustard gas. So it's mostly it's 2 chlorines, 1 sulfur, and each of these corners, that corner, that corner, that corner, that corner, those are carbons. So it's Cl, carbon, carbon, sulfur, carbon, carbon, and chlorine again. And the carbons have hydrogens on them too. But it just takes forever to draw all the carbons and the hydrogens, so the shortcut is just to make them little corners. But yeah, so that's mustard gas right there. Yeah, it's kind of nice. Like a lot of those, it's kind of sucks. I like organic chemistry because it's pretty cool learning how to draw those things and like write the names. It just looks cool too. But something like because it gets tedious. So if I just draw propane, all right, here's propane. Propane is 3 carbons and 8 hydrogens. And instead of just doing this, you could just literally do that. That's propane as well. So each corner is a carbon, 1 carbon, 2nd carbon, a 3rd carbon. And then you just assume that since carbons always have 4 bonds, they just always have 4 single bonds, that they're surrounded by hydrogens. So this one has 3 hydrogens, this one has 2 hydrogens, that one has 3. So it's just a quicker way to draw organic molecules. So yeah, if we have time at the end of the year, I don't know if we will, but I usually like to spend a couple days on organic chemistry basics because it's pretty cool. You get to learn how to name really long, crazy organic compounds and all the functional groups, things like ethers, alcohols, aldehydes, lots of cool stuff. Oh, you could do it that way too. Yeah, so that's the thing that gets kind of tricky. You could do it the inverse way as well. It doesn't have to be like a mountain. It could be like the letter V. Like, I'm trying to think. Yeah, it gets kind of cool. Like 1, 2, 3, 4, 5. And let's say I've got a chlorine here. It gets kind of cool. Like something like this, if you want to name this, you have to see where all the carbons are, so all the corners basically. So 1, 2, 3, 4, 5, 6 carbons, right? Because 1, 2, 3, 4, 5, 6 corners. And so you have to number the carbons, just in case if you're interested. I don't know if you are or not, but 1, 2, 3, 4, 5, 6. So you number the carbons, and you start the numbering closest to any branch. Like there's a branch here for chlorine right there. So we start the number 1 closest to whatever branch we have off to the side. And to name it, you have to name where the branch is first. So on the 2nd carbon, there's a chlorine. So you start off by saying 2 chloral, We're not done yet. But that's just the beginning of it, 2-chloral. And this is 6 carbons, so that's hexane. So yeah, this would just be 2-chloral, 2-chloral hexane. Yeah, something kind of like that. And it gets way more complicated because you get these other groups that start to branch out, like other carbons that might come down here, like some other zigzags, and it gets kind of cool. It's almost like Lewis structures, but to an extreme. Like it's like extreme Lewis structures. It's fun, but I usually like to do it at the end of the year. But the way things are going with the virus, I'm not sure if we'll have time or not. But it's pretty cool, and it's useful, especially if you want to go into OChem or anything. Yeah, they get kind of complicated, and like what you were saying before, I just erased it now, but it could be that I could have drawn it the other way, and it has the exact same name. Yeah, so it gets kind of complicated. There's like some really weird ones. I'm seeing 2-chloral. Yeah, like here's. No, let's not do that one. Yeah, like this one, oh, that's kind of bright. I don't know if you can see that or not. They actually, for whatever reason, they put the carbons with their hydrogens here. They didn't have to. They just could have made it corners, could have kept it as all corners. But since there's a chlorine here, and let's see, here's 1 carbon, 2, a second carbon, 3rd carbon, 4 carbons. So you have to look for a carbon chain, the chain of like the backbone of all the carbons. So 1, 2, 3, 4. So it's a 4 carbon chain, which is bute, or with no chlorine, just with H's and carbons, it's butane. And so you start the numbering closest to a branch. So here's a branch on this side. So we call this one 1, 2, 3, 4. So on the second carbon, there's a chlorine. So this would be 2-chloral butane, because bute is for 4 carbons. It's like a lot more prefixes to remember. Like meth is 1 carbon, eth is 2 carbons, prop is 3 carbons, like propane. Bute is 4 carbons, like butane, and then octane is 8 carbons. So yeah, it's like a crazy. It's kind of similar to Lewis structures, but the process is a little bit more complicated. It's just kind of cool because when you write the names out, it looks. It just always looks really satisfying when you're done with it. You have like some really long name with all these dashes and numbers. It's kind of cool. Yeah, I don't even know if they go that much in depth in it in OChem, because in OChem they might do some of that stuff, but it's not too complicated. No, yeah, just because carbons always have 4 single bonds around them, so like they don't matter in the name at all. Like so like I'll just draw butane again really quick. So butane is 4 carbons. This is just plain butane. That would be the only name of this thing, just butane. But each of these hydrogens isn't like a branch, kind of like the chlorine I drew earlier was a branch. But hydrogens are just implied to be here, so you don't consider them branches. They don't affect the name at all. And like I said, you could draw it like that, or you could draw it like that. These are all the same thing. This is butane. It's 4 carbons, right? 1, 2, 3, 4. Yeah, these are all butane. Just different ways of drawing it. Obviously, this is probably the quickest way. One of these, instead of doing all the H's and C's and stuff. So, yeah, organic chemistry is just the chemistry of carbon, basically. That's what organic really means. It's just carbon. Yeah, that would be cool stuff to get into. We just have to do thermal chemistry still, reaction rates, and acids and bases. So 3 more units. So we might not have time to get to OChem. Usually with OChem, I don't even make it a unit. I just make it like a little mini section of just a couple of days. And they're just like bonus questions on the final. Just because it's really complicated stuff, as you can tell, it gets kind of complicated. So if OChem at the end of the year, it's usually like maybe 2 or 3 days, just as like bonus little stuff, and then they're just like bonus questions on the final. So if you didn't understand it, like you're fine, kind of thing. They do a little bit. I don't know how much in depth they go. I've never taught AP Chem. I just did AP Physics. But in AP Chem, I know they do a little bit. I don't think they go into too much depth with the naming, but they definitely do a little bit. Typically, like, because organic chemistry can get really long and complicated, but they probably stop with these things called functional groups, which then get involved with those namings and those structures. So functional groups are just different types of organic molecules that have very specific functions and chemical reactions. So there's different groups like alcohol groups or any groups with an OH attached to them. And then, like, for example, like 1, 2. So an alcohol is anything with an OH. This is one functional group, for example, anything with an OH at the end of it. And F means 2 carbons. So it just affects how you name it, right? So, like, for example, the prefix F is 2 carbons, and alcohols end with OH. So we have 2 carbons here and then an OH. So we call it ethanol, kind of like that. And then, like, yeah, so they pretty much go as far as like that kind of stuff if they do anything. But even then, I don't know if it gets too in depth. Yeah, they probably don't spend a whole lot of time on OChem. I'm sure they touch on it a little bit though, but they probably don't get too much in depth with it. But it's kind of cool, like all the prefixes, like so, like, I mean, it goes all the way up to 10. There's 10 main prefixes here, but meth is 1 carbon, eth is 2 carbons, prop is 3, bute is 4. That should be a 4. But you can figure out the basic organic compound structures with these things with a formula. So, and so these are if they all have single bonds. If they all have single bonds, they're called alkanes. So I've just been showing alkanes here just for fun. I haven't been showing alkenes, which have double bonds, and alkynes, which have triple bonds. So alkanes have single bonds only. And to figure it out, you just have to plug stuff into this formula. So if it's a methane or ethane, and they all end with ane because they're in the alkane group. So it's like a lot of stuff with suffixes and prefixes in OChem. So if it's methane, that's 1 carbon, and then 2 times 1 plus 2, which is 4 hydrogens, right? So CH4 would be methane, and it makes sense because carbons always have 4 bonds around them. And so if it's only single bonds, if there's no double bonds, it's going to have to look like this, right? So this is methane because it's 1 carbon and 4 hydrogens. So yeah, if you put a 4 here, butane would be C4H10, right? Because you get 8 plus 2. So that just kind of helps you figure out what the formula is going to look like, basically. Yeah, it kind of gets kind of fun. I enjoy doing some of that stuff. Sometimes it gets difficult grading because sometimes people's zigzags look kind of hard to decipher and stuff. So it can easily get thrown off. So yeah, I mean, you could call it that too. You could call it that as well. With some of these molecules, they tend to have more than one name. It's just easier to call it methane instead. Like, yeah, so Yeah, so with alkanes, they just have single bonds, and it's like that formula here. So they all end with ane. If you get to alkenes, those have double bonds. So those would be like methene, or which actually wouldn't exist because it's just hydrogens, and hydrogens can't have more than 2 electrons. So there's no such thing as methane, actually. My bad. But then alkynes have triple bonds. So like, yeah, I mean something like this thing here is decane, because dec means 10 hydrogens. So this is decane, right? And then it's double the hydrogens, twice as many hydrogens as carbon plus 2, so 22 hydrogens. But that'd be really hard to draw, so I would just do a zigzag instead. It's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But of course, it could get flipped. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 10. So yeah, that's like decane. It's the long zigzag structure, because that's just way quicker than doing 10 carbons and 22 hydrogens all over the place. And then, yeah, it gets, sometimes the naming can get weird because you could have something like this, and then maybe there's like a random double bond, between the second carbon and the third carbon. And then when you name it, you have to specify where that double bond is. Yeah, we're probably not going to have time for that stuff, though, this year. Yeah, let me know if you have any other questions, though, or anything. I might probably head off in a little bit because it seems like there's not anyone else here, unfortunately. That's a good question. With AP Bio, I'm sure there's a little bit, but if there is any, it might involve some basic OChem stuff. Excuse me, just because organic chemistry, the chemistry of carbon, is the basis for things that are alive, biological organisms. And just they're really just molecules that are useful for living things. They're byproducts of living things, or the things that living things use. But yeah, I'm not sure. There's probably a little bit of OChem. Yeah. Oh, okay. Never mind. Well, I just looked it up online. It looks like there's not much chemistry in AP Bio, actually. Maybe they just want you to have a little bit of a foundation of understanding how things work, but like certain things like pH, like acidity, which we still have to go through. That's probably gonna be the last unit. And just knowing about like chemical bonds, but not much. Yeah, not too much. I mean, there might be some stuff about just knowing what a chemical reaction is, which is pretty basic. Things like photosynthesis, cellular respiration, those are all chemical reactions. So you might need to remember how to balance it. For example, they might give it to you and you have to like balance it maybe. But it doesn't look like there's that much chemistry in AP Bio. So probably just a little bit of stuff with like looking at molecules and chemical reactions, and maybe just knowing about pH, which is the scale of acidity and how acidic certain substances are. But yeah, it's not too much. So yeah, probably no OChem after all then. Yeah, because even AP chemistry doesn't do very much OChem. I've never taught AP Chem. I just like to throw some OChem in at the end of my normal chemistry class just because it's fun. And it's usually just bonus stuff anyways. But yeah, so it doesn't look like there's much chemistry in AP Bio. Although, yeah, it's probably really basic stuff like valence electrons, balancing equations. I literally just saw this link on Google. It's like 3 minutes, and it's just talking about the basic chemistry for AP Bio. So that might be helpful too. Yeah, I'll probably take off in a minute or so. Let me know if you have any other questions or anything though. All right, sounds good. Well, hope you and your family stay safe. I'll probably do another live stream tomorrow, but we'll see how much people show up. But yeah, have a good one. Take it easy.